Welcome to another video where I work on Plum, a new programming language. In the last video I created a new virtual machine called Ground. It can execute programs, and there's a program that adds 2 and 3, and the result is 5 as a little endian encoded 64-bit integer number. The actual ground program looks like this. So this is a simple bytecode where we have one byte that tells us what we want to do. We want to push an 8-byte, aka 64-bit integer. That's what this C2 means. And then here's the integer afterwards, those 8 bytes. And then we want to push another integer to the stack, this time this one. So now we've pushed the 2 and the 3 to the stack. And A0 is an arithmetic instruction that adds these two numbers. And finally F5 returns. And because there was no call before, this actually exits the program. Alright, so I've created that as somewhat of a compilation target for Plum, the programming language, which currently doesn't quite use that. Plum looks like this, and it currently compiles to bytecode that looks like this. Oh, hang on. Let me get syntax highlighting working. Alright, so yeah, Plum internally also has a virtual machine, which is implemented in Martinez, my previous language, the same language that Plum itself was written in. And basically I want to have a clean cut somewhere. I want to have this one serialized format that everything goes through, so that I can store these programs somewhere and switch out the backend later on and stuff like that. So that's why I implemented the other VM in Zig. Which means that now, rather than having these bytecode instructions floating around in memory somewhere, we actually want to serialize them and put them in a file. That's what I'm going to work on today. Alright, so I'm not going to call this VM, and we'll actually not have code in here for executing the code. Okay, none of this, pushing, popping, allocated memory, crashing stuff. Nope. Instead, we also don't need this, any of these, or these. Printing bytecode still sounds useful, I guess, so let's keep that around. But basically, we don't execute the bytecode in Martinez itself. Alright. Which means I'm actually going to rename this file into bytecode. Okay, so the virtual machine internally code runs in a stack-based virtual machine. The bytecode. Just bytecode, I guess. In a stack-based virtual machine, something like a mini computer implemented in software. So stack and call stack and operates on instructions called bytecode instructions. And the bytecode that Plum compiles to is called Ground, also created by me. This repository contains the specification of the bytecode. Feel free to write your own interpreter to run Plum programs. I think that's actually like a really nice exercise, taking that specification, writing an interpreter for that, and boom, now you've kind of unlocked the ability to run programs. yeah, I'll probably like publish my Zig interpreter at some point. But as you know, then I would like to clean that up and give that a license and a nice README and stuff like that, which takes some effort. Okay. Figure 1. Great. Okay, so the engine is on. Yeah, I think this is like that was part of the ground specification, not what I'm doing here. Okay, so I think we'll actually have a struct in bytecode that then has instructions, which is a slice of bytecode instructions, so that we can really say the code compiles to bytecode. Boom, that's this. Bytecode instructions are these. Oh, hang on. Actually, I think it makes sense to call this ground instructions. Yeah, that does make a lot of sense. Ground is a bytecode, and yeah, sure, for Plum it is the bytecode, but still, that is a bit more the ground bytecode. Okay. I did kind of move around the instructions in the definition, like comparison stuff with a single. Yeah, arithmetic stuff. Let's move that over here. Then the binaries, bitwise, not binary stuff, bitwise stuff. Like AND or XOR. Then the stack control stuff, you know. So these are organized by the letter, like A, B, C, or C, you know, stack control. I don't know, C is kind of far-fetched, I guess. Push padding, push 1, push 8, push these, and pop stuff. Yeah, then we have control flow, which is F actually. Yeah, and also C, D is data stuff, this one. Then we have E. Now they're in the same order that they are in the ground specification. Alright, which actually I'm also going to open. Yeah. Okay, so we do have an additional NOP instruction that does nothing. I think we don't really need to omit that. But still, I guess for completeness, let's have that in here. And also I added some instruction. Yeah, let's just go through them, I guess. Let's split the editor maybe and have that in here. Okay. So with NOP we have add 8, we have sub 8, we have mul 8, we have diff 8, we have mod 8, we have compare 0, 8, then we have end 8, or 8, XOR 8, we have push padding, push 1, push 8, push 1 from stack, push 8 from stack, pop, and pop below top. Then comes malloc, free, store 1, store 8, load 1, load 8. Oh, hang on. Let's put this one before the others and before the jump instructions. Okay, yeah, so we have crash and jump, jump table, hang on, yeah, jump table, call, then we have push indirect, and then call indirect. call indirect and return. Okay. Nice. And these description here, they are not only not up to date, but also like you should just have the spec and read the spec rather than having these kind of ad hoc definitions that may not be super complete or correct if I change stuff. So I just kind of want to remove these comments. Yeah, I think that works out. Boom. Oh, okay. Whew, that's a lot cleaner. And maybe add an explanatory comment, ground instructions. The ground instructions, see the ground spec. So this repo for explanations. Amazing. Okay. Pretty nice. Okay, I think this is all fine. This as well. Pop below top. Actually, only has a byte in here, I believe. Pop also only has a byte. How many should be skipped? And how many to pop? Then we have malloc, free, store, load. Crash, jump to an offset. That's an int, not really an address. And jump table as a slice of ints. Amazing slice. Yeah, makes sense. Then a call of an address, push indirect of that. Okay. Nice. Then we have printing ground instructions, but also probably just printing the ground. And that will just print all the instructions. So we'll print, I guess, the instruction like that. Pretty cool. Actually, this will be an index, I guess, into the instruction. Instructions array. Yeah. Just so that I don't forget this, I'm gonna write that on each of these. Okay. Yeah, push padding. I think that also only takes a byte, because you can then have multiple push padding instructions if that's not enough. All right. Yeah. Cool. Cool. Yeah, the not instruction was added. That's just gonna be nop. Yeah, like useless instructions, they are prefixed with this. So yeah, if these are all the instruction index, then I think it makes sense to also print the index down here. So basically enumerate these, and then this is really like an entry or something. No, and entry dot item, that's the instruction, and entry dot index is the index of the instruction. And let's let's format that and pad that to like, I don't know, 4 places or something. And then print that ground thing after that's been created. Equals bytecode. Yeah, compiling a module results in a ground program. That's pretty cool. And then you should just be able to do, you know, print ground. Yeah, running does not happen in here. But instead we do serialize ground. Result is result.data.toReference. Nope. Nope. Okay, yeah, that seems a bit cleaner, you know. Yeah, this is called toGround, so let's actually give that a nice proper name. Waffle toGround, and then Waffle toGround is this compiler stage. Then we'll also have to import here. Yeah. And the function here is called toGround. toGround of the Waffle returns ground. Okay. We need to generate, yeah, I guess ground bytecode. We have a GroundBuilder, which instruction has a corresponding function that appends the instruction to the instruction buffer and also updates the state model. Yeah, except some instructions where you have to manually adjust the stack. Okay, so this really is a GroundBuilder. These are ground instructions. Amazing. Amazing. The patch will actually be just an index into this list. That's pretty cool. And then fun bytecode builder. I guess fun GroundBuilder. Emitting an instruction. Okay. No, not really. We can just, like, this buffer can grow. And that's fine. Even like before that didn't work, for example, because the patches, they had references to the actual instructions within that list, so we couldn't allow that list to grow. Now though, that shouldn't be a problem at all. Yeah, builder.instructions.push. Okay. Nope, doesn't change the stack at all. Here we have, oh yeah, let's shuffle these around. So we have int and bitwise instructions first of all. Then we have push padding, push one from stack. We have pop amount. 0 minus amount, which is a byte, so we need to convert that to an int, similarly here. And then pop below top, takes the tuple, and then how many to pop, which is a byte, which needs to be converted to int. Okay. Yeah, I need to update the stack manually. Called indirect, but also push indirect. That pushes a function pointer. Yeah, then we have return, we have malloc, we have free. Yeah. Like crashing should be supported. Yeah, I don't know. We'll get to that, I guess. Yeah, copy from stack does something. Yeah, ref of next. Let's not do that. Let's have index of next maybe. But that is literally instructions.len, so nope. Okay, because this can grow, like we can compile arbitrarily long programs, crazy. We can now, we don't need to initialize that and reserve memory initially. Okay, then we have the Waffle fun. That gets compiled with a builder. And then for each of the patches, well, what we do is we take patch.where is an index into the instructions. So I think we'll need to take, we need to get that instruction and switch on that. Yeah, just get a reference to that instruction maybe. Yeah, switch on the instruction, and if that is a, like what instructions may need patches, these kind of jump table instructions, whatever. Jump. In that case, we do this should be mapped to a ground instruction jump using the actual new address. Let's adjust the patch maybe. Yeah. Let's say that the patch not only has a where, but also a what. And then patch what is an enum that is either, that tells us what this instruction should become. It should either be a jump to that signature, or a jump table with a slice of signatures that we want to jump to. Stuff like that. Or a call. Or you push indirect. Actually, I think these are only used within the same function, so we don't need to use them. I think. Not entirely sure. Yeah. Let's maybe leave it at that and see if that is enough. Okay, so signature to address. is a signature to offset. Put instructions.len in there, simple. We switch on the hatch dot what. Yeah. If that is a jump with some target, then we do instructions dot yeah, pretty much this. But it can only be like a call, I think, and push in the left. Oh, and this should be a call. Nice. And then we can set patch.where to that new instruction. And let's not call that new, but patched. Pretty cool. Pretty cool. Yeah, like this is kind of horrible. Well, oh yeah, and this is just the offset of the main function. I think we actually want to put the main function at the beginning of this bytecode. Okay. Yeah. This looks fine. This is beginning to take shape. And then in the end we'll return ground, where the instructions, our instruction is converted to a slice. Amazing. Okay, then for these, let's see, we have GroundBuilder. We can compile stuff, adding mappings. Okay, sure. And we can compile Waffle expressions. Perfect. Hang on. Emitting instructions. That, I mean, that makes sense. But this up here, this light. Each instruction has a corresponding function that appends the instruction to the instruction buffer. No, no, we just have an emit function. Well, so you can rather say we have a GroundBuilder. Its emit function pushes an instruction to the instruction buffer and also update the stack model. Perfect. Okay. Yeah, because we only have these kind of emit functions in here. Okay. Okay. Yeah, this is not working. Like, this will not compile. Because in several places we're just doing, like, we're passing ints to somewhere where bytes were expected and stuff like that. Exactly, the VM file doesn't even exist. Yeah, these simple problems. Oh, hang on, that is the ground actually. Nice. Yeah, exactly. So push padding needs an int. push padding. We have an amount. Okay, yeah. I think we'll need to split that amount up, possibly, into multiple push padding instructions. Yeah. So basically we want to loop. And if the amount is larger than 255, then we can't encode that in a single instruction. Then we'll just emit a push padding instruction of 255 as a byte, the lower byte of that integer, which should just be the same number. And we will then say amount is amount minus 255. Else we will push an instruction for the rest of the amount and we'll break. And this is also guaranteed to take the entire amount because we've checked that the amount is at most 255. So it fits in a byte. Nice. Yeah, no. Oh yeah, this is very true. I think we have that at some places actually. No, maybe not. Okay, cool, maybe not. But here as well, pop below top. And we have that in several places. Oh yeah. So I think it makes sense to have, it may make sense to actually have kind of helper functions for these. You know. Oh yeah, here as well, the align too. Okay, let's do like a push padding and builder. Where you can push an int amount of padding. That's pretty cool. And that works using exactly this. Let's just this builder dot push padding of that int amount. Yeah, which results in potentially multiple push padding instructions. And then here we can just directly say, hey, please push padding. And we also don't need this actually. Maybe it makes sense to have like bespoke, you know, functions for the individual instructions. And they each do some like instruction-specific optimizations, if possible, like like actually pushing multiple instructions. Yeah, I think that makes sense. So we have these simple instructions like nop. Yeah, that's cool. Nop that pushes nothing, and that just does builder.emit Nope. And for these kind of instructions where you also have to update the stack manually, that we could also enforce that you have to pass that in here. Yeah, like that. Okay, you know what, that's... I'm thinking about removing these functions and only having these very simple root functions. So I'm actually not going to use them in here. I'm just going to do builder.instructions.emit and builder. Yeah, the stack size is unaffected. Simple. The next instruction is add 8 using a builder. Functions call bound instructions. Boom. At 8, which looks pretty similar. Builder.instructions dot push is what it's called. Push the add 8 instruction. But then we also put this in there. We add 8 to the stack size. Oh, hang on. No, for add that was -8. Yeah. Okay, I like that. So we have add, we have sub, and you're adding a new instruction is then not jumping around in all these different functions, adding cases. It's just add. You add a simple function that pushes the instruction and updates the stack, and that's it. And you can do optimizations in there. You can say, oh, pushing a padding of 0, it actually does nothing. You can add more higher level instruction functions for that. Stuff like padding with more than 255 bytes, stuff like that. Yeah, it's gonna have the mul instruction. They will have a div and mod. Oh, you know what? Really, really cool. The add instruction, actually. I think I'm gonna do -8 plus 8. To like really, hit home that this consumes an integer, consumes another integer, pushes the result. Oh yes. Not doing that in my head, just. Okay, mod 8. Yeah, same thing, actually. Okay, yeah, compare 0. Because this is interesting, -7. And rather than having a -7 there and being asked, like, why that? Now you have compare 0, 8. And you can see that it consumes an int and then pushes a byte. Oh, that is nice. That is really nice. So we have these. Then AND or XOR. What the hell? And or XOR. Okay, we have push padding with some amount. And this amount is just a byte. Builder instructions push padding of that amount, and then it's also builder dot stack size. Nice. Next, push 1, push 8. One takes a value, which is a byte, that increases the stack size by 1. We have 8, which takes an int that it pushes, increasing the stack size by 8. We have push 1 from stack. Push 1 from stack. And yeah, we could just put the offset in there, like every time that is used. Push 1 from stack. Yeah, we have the offset. Copy from stack from some offset. Yeah, we like in the push 1 from stack, we have -1 in here. Here as well. So I think it makes sense to have actually accept the start offset. Then this will actually take the start offset -1, maybe. Same in the 8 case. I don't know, maybe there's a better version that doesn't even rely on passing offsets around, you know. May change that. Okay, so then there is pop. So amount is a byte. Yeah, it just does that kind of thing. Yeah, pop below top. This is really readable. You know, you have the amount of bytes to skip, and then the amount to be popped. Yeah. Rather encoding things first in these tuples and then passing those around, we just have named function arguments, and then only at the last moment, you know, they are kind of turned into these. Okay, case jump. takes a target how does it change the stack? Well, not really. Okay, makes sense. Jump table. Mm-hmm. And it consumes the byte and that tells it where to jump. Okay, we have call. You need to update the stack manually, like that is... Now you don't need to remember that. No, we can just say we have call of some target and stack diff is an extra parameter that is not used for the call instruction, but that is instead used for this. Nice. Then push indirect. And call indirect. That is also going to take a stack diff. Maybe it makes sense, you know, like every indirect call definitely consumes the target, which is 8 bytes. Maybe it makes sense for the stack diff to only be kind of the stack diff of the called function, not including, you know, popping the function itself. We have return, which is actually called return, not ret. Gotta change that. Well, then malloc free start and load and crash. Malloc -1. So I don't remember where that comes from. But if I just write, I don't know, malloc consumes an alignment, it consumes a size, and then pushes an address. That's a bit more clear. Yeah, free has changed in the new bytecode. Free consumes a lot actually. The alignment, the size, and then the actual pointer. Then store 1 and store 8. Yeah, store 1 does something. -9. Oh yeah, because it pops the value and then the address. Star 8 on the other hand, that does this. It pops the value and the address. 16 then is load 1. Which doesn't pop that. It pops the address and then it pushes the value. And of course there is load 8, which pops the address and then pushes something. And I'm gonna leave that here, even though this does nothing, this entire line. But it is, this does affect the stack, and I think it's useful as some sort of documentation to have that here. Okay. Nice. This is really nice. Yeah, return, we gotta handle that. Like that. Cool. More advanced macro instructions is how they usually call them in assembly, and that actually consist of multiple instructions. Here's another sentence. Push padding of some amount. Oh yeah, we just do push padding of this byte. Okay. Same here, we just do push padding of that amount. Oh, we can even put some optimizations in here, probably. I mean, NOP doesn't need to do. We don't need a SNOP. We don't use NOP period, so we don't need to have that function even. And here I would say if amount equals 0. Oh, okay. So pushing padding. Basically we want to check if the amount is 0. If that's the case, then we'll just return immediately and not do anything. Yeah, same with popping. If the amount is 0, then we'll just return immediately. Pop below top, if the amount is 0, then we'll just return immediately. We can also check if the skip amount is 0, then we'll just emit a normal push instead. Builder dot pop. Yeah. Okay, jumping, jump table, call indirect. Oh yeah, push indirect, call indirect. Okay. Alright. Then macro instructions, which are actually multiple other instructions, potentially. So there's push padding with an int. This just does the pushes padding, yeah. These we've kind of integrated them into the code above. Okay, yeah. what's going on here. Oh yeah, all of the emit calls, they are broken now. Yeah. There are no definitions named emit. Yeah, very true. So let's go to push 8 from stack. I think this is, hang on, I think the push functions, yeah, we've added this -1 and -8 thing, so that we actually only need the offset, not that one. That's great. Then push 1. Then oh, hang on, what did I do? This doesn't seem right. What was that before? Push 1 from stack. Yeah, that makes sense. And this will just be a pop below top. Nice. And this will be a return. This is pop below top. This is push 1, push 8, copy from stack. Pop below top, boom, boom. Oops. Yeah, jump table. This is just a placeholder. I see. Yeah, not sure about that one. Guess that's fine. Oh yeah, here, that is actually updated. I see. I think I'll do jump table. Ref of next does not exist. Instead we have a jump table index. Then we push the instruction, and then we can say, yeah, builder dot update maybe. That would make sense. Update that. Oh. Patch jump table maybe. And these are just ints and jump and jumps. Yeah, sure. So in the table we push the instructions len. Then we have this, and jumps is the length of that. Call ref will be call index instead. And we have this builder.call. Oh, hang on. think we can actually call, instead of having this and then overwriting that, I think we'll actually have call, which takes a target. Yeah, so the target should be a string. It pushes a call instruction 0, which is just a placeholder. And then it does builder.patches. Oh, I think there need to be ampersands there. Not entirely sure. Yeah, but basically for calls, we want to push a patch that looks somewhat like this. So calls, where are they? Here. Really, that is that. Index is builder.instructions.len, and then where is the index, and this is the target. Amazing. Let's call that signature. Sure. Wow. Like that is actually makes sense. Oh, hey, this is a patch. What call using the signature. And then we have patch call on a builder with an index and an int. And that just is builder.instructions.set the instruction at that index to the ground instruction call of that target. Amazing. I like that. Also a patch jump. Let's maybe put a jump placeholder. Because I think every time we have a jump, jumps only jump forwards in the code, because we don't have loops. That means that we only place placeholders where we don't know the target yet. So we'll just place a jump with a 0, and we return the index, which will be builder.instructions.len, and that is what we return. Yeah, then we have a patch jump that actually has an index, which is an int and a target, and then it sets that instruction to jump to that target. That makes sense. Same with a jump table. We have a function for emitting a jump table placeholder. And then patch jump table of a builder with these targets. We'll then actually put the instruction in there. Oh yeah, this one returns the index. Yeah, this is looking pretty cool. This is looking quite amazing, actually. Push indirect. We don't know the target here, so let's turn this into a signature one. Yeah, and what we do is we do this. That's a placeholder. Nice. And we'll store the index. And then we say something like this. Put a patch in there. Let's remove that. And then cool. A lot of patches that push a patch. Push indirect of that signature. Quite nice. Yeah, okay. That looks so nice. Yeah, let's remove these ones. Okay, jump table. Placeholder. No need for this comment, no need for that. And this can just be that. Crazy. Yeah, and here we just have patch jump table. Same here, we just have jump placeholder. And that is actually the index, so we don't need builder instructions.len. We just push the placeholder in there. And then we have builder.patch jump of that jump and jump to the end place. Nice. Then we have a call. Exactly. We put nonsense in there. So now let's change that and actually put the function in there. And this also takes the stack diff. So that really makes sense. You know, this is the call instruction, which affects the stack in this way, and then we have the pop below instruction. Nice. We don't even need the call index, because the call immediately pushes the patch to the patches thing. This will be a call indirect, and then we emit a popular top of that. Oh, hang on, call indirect. Target doesn't even make sense. Yeah, no, it does make sense for push indirect, but for call, not really, because the target is popped from the stack. Yeah, yeah, let's do -8 in there because the target is popped. Then this is only need to care about the stack diff from the call itself. So that would be this one. Hang on. Yeah, we take the original stack size, -8, is because it consumes the function pointer. Hang on. The function consumes the padding. Does. I need to double check that. That may be the maybe the reason some things go really wrong at some point. Okay, yeah, function pointer of some signature. Oh, look at that. That is actually builder dot. Yeah, no, that is its own instruction actually. Builder push indirect of the signature. Just that. Nice. Yeah, this is just nice. And then malloc of a known size. And yeah, compiles the size. Okay, sure. Oh, the alignment is always 8. Sure. You know, let's put some spaces in there maybe. Also align these. Yeah. Oh, that is cool. Oh yeah, this does change. So we have a pointer to change the waffle so that it also gives us the size and alignment. Yeah, that is something that would prevent stuff from working, so I really should have to-dos in here. Okay. Okay, here we do something. Have a load and store copy the data from the heap, we just have a push 8 from stack. Not sure what about this, but meh. All right, compute the data to be boxed. Build a line to 8, sure. Yeah, I don't know what exactly is going on here, but let's just gradually simplify that, and then things probably become more obvious. Oh yeah. Oh, because pop only works with an integer. True, because we have this kind of macro instruction only for push. Not even that, only for push pay. I see. Let's do something very similar for popping. Pop some amount, if the amount is larger than 255, then we just do that, otherwise we break. Kind of simplify this code. Maybe I can say if amount is less than 256, then break, and let's do this, and then I can do this after the loop. That kind of allows me to, you know, do this kind of thing, which is kind of like a while loop if you squint your eyes. Yeah, I think that's a bit cleaner. Okay. Oh yeah, pop below top, similar thing. push indirect. Push indirect does need that, but we are gonna call indirect function. Crash does not exist apparently, although it should. Before all the jump stuff. Oh yeah, the ordering is like a bit messed up. Let's go with the arithmetic one. Yeah, first have add, then the binary stuff, the B stuff, then C, the control stuff with pop and so on. C, then D, aka the data stuff. And then E, aka crash. No idea. Okay. Then structures.set. That is not a mutable list, indeed. 240. Hang on. Oh yeah, we can do that. We can do that even nicer. We can say builder dot patch call, I think, at the patch dot where let's see. Yeah, maybe not. Maybe. Sure, let's just have that in there. Okay. Also, this is not really used, I guess. So, nice. Oh, and the Plum file. This returns ground. Beautiful. That's clean. Okay. We're slowly getting somewhere. Where's that? Like format, maybe? Oh, very true. Okay. Byte and int around 65. Yeah, no, let's not special case these because they are not very common. Actually, that never appears in the code, so I think it's fine to just not special case them. heading. In this case, it evaluates to nothing. Previous cases, aka the previous case, to nope. Okay, that seems to do something. Yeah. Okay. It's a copy from stack. In here probably. Okay, yeah, that is defined. And this is the thing where that's where that thing starts, basically. Yeah, I guess offset is fine. Oh, that's it, just for locals. Okay, so we have a local expression. With offset -32. That does not seem correct. So this is only called from here. So build that up, find distance from top. Of that ID, that is not the correct thing, apparently. That does seem correct though. Okay, so let's maybe print whenever we compile an expression. I think we need to provide yeah, the surrounding Waffle fun and also an indentation, because of course we do. Okay, expression number 4. Okay, so we are compiling 003. We'll probably go through the functions the same way that they are printed here. And indeed the first expression is 003. So we compile the inner expression 0, then we compile this giant switch thing, which means that we compile this one, means we compile this inner one. Okay, Yeah, then we compile that. In order to do that, we compile this. So then we compile that. We compile this call. We compile malloc. Store. Okay. And this doesn't work. Okay. Let's maybe compile. Hang on. Every local is compiled. Let's maybe print local. No, local is at build a stack size, at least at this point in time. Yeah. Okay, so 4 is at 32. Sure. Compiling malloc. I'm just checking. These emit things, they take immutable function builder. Okay, I get that. And they build out instructions. The push instructions is, oh, it is a pointer, it's a mutable list already. So that's why this works. Okay. And they assign the stack size, that makes sense. Yeah, here we don't need that. The patches is probably a reference, yeah. There's already a reference to a list, so we don't need an ampersand there. This doesn't work, okay. Yeah, no. Let's also always print the stack size. Let's see, we compile the local variable 1, which is at stack size 3. That's crazy. Is it really? I don't know. So we're looking at a cast function, casting this thing. Oh yeah, because the arguments are 3 tags. So this expression indeed is at offset 3. 3, okay, yeah. And then we've compiled this one. Local 8 is at 8. And this one, okay, because this results in something that has to be 8 aligned to 8 bytes. So we add some padding. Yeah, we have these 3 bytes, here another 3 bytes, 2 bytes of padding. Here we have this at offset 8. Makes sense. Yeah, so then we are compiling that. Stack size is 8. Makes sense. To do that, we're compiling this one, this one. Okay, sure. Yeah. Oh yeah, this local 2 is also at 8, because like we compile this one, then we do a jump table, switch on that, and then that consumes this byte, and then we do this at size 8, so that whatever this results to is automatically what this entire thing evaluates to. So this is at offset 8. This thingy here is exactly 2, yeah, that is at offset 8. So that thing is at offset 8. So the 1 is at offset 8, makes sense. Okay, so then the size of that, will be 2. But this right here has a requirement of 8, alignment requirement of 8 bytes. So this is, we add some padding, and then we compile that to offset 16. Makes sense, stack size is 16. So we are compiling the 2, stack size is 16, okay, sure. And 4. Yeah, this has to be 8 bytes aligned. And this is like 9 bytes. I'm at offset 16, so we need to go to offset 32 to deal with the malloc. Then we compile the malloc, stack size is 32, correct. So we're compiling the internal thing, we call malloc, great. Then the store, which will be 8 bytes later, because the malloc returns an address that is 8 bytes in size. Local 5 is something, okay. Is it 40? Yeah, we're compiling this one right here. To do that, we're compiling the aggregate. And then the 1 and the 3 and the 4. Look at that, that works. Nice. But then local 6 is at 0. Why is that? That doesn't make any sense. So this store right here, apparently that doesn't behave correctly, maybe. What are we doing? We have let's move that there, because that padding only exists for the pointer. Oh, I see. Yeah, push 8 from stack. We don't need these -8 things here. And same here with the push 1 from stack. We don't need the -1 there. Okay. I mean, yeah, same error, but yeah. So push 8 from stack. I mean, let's push 8 from stack. That is always, yeah, always this kind of builder stack size minus something, right? Yeah, let's replace that. Let's change that so that it actually takes the start. But that is not the offset from the end, but it's just the absolute start position. And then what we do is we take the builder stack size minus that. Yeah, and this gets a bit simpler because we can just say let's push the pointer to the stack. Oh dang, that is actually readable. Like this. And here we can say let's push the pointer to the stack. Let's push the data plus cursor to the stack. Wow, readable code. Crazy concept. And here on this is also used in here, isn't it? Inside this. Yeah. It is just the start index, I guess. Nice error message. Yeah, if the size is less than 8, yeah, then we break. Otherwise we push the start. Oh yeah, we basically want to have some sort of cursor. It starts at start. 0, I guess. Yeah. And if the cursor, hang on. Plus 8 is less than the size. Otherwise we do start plus cursor. Push that. Yeah, and then we say cursor equals cursor plus 8. Nice. Yeah, there's not find distance from top, but this is just, nope, just, oh, just that. Oh, that is nice. We don't deal that much with like relative stuff. Yeah, just use that. Nice. Assembling. That's not good. I kind of got stuck there. And the cursor's always incremented in here. So compiling this, stack size is 3. Okay, so the cursor is getting quite big. Why is that happening though? Try to be really quick. Too slow. Oh man, yeah. Well, okay. So maybe not that. What do we want to do instead? Like, how can the cursor be so... Okay, I think there's like an off by 1 with the size. So let's assume the size is 0, for example. Then the cursor is 0, cursor plus 8 is less than size. Oh, there should be a greater. Okay. Yeah, okay. So why is that at 0? I don't get that. Maybe I should add some sort of emit function just so I can more easily debug stuff. Compiling for stack size is 56. Okay. Let's compile the locals. Okay, after compiling an expression, the stack size should never be, like, it can be greater, but it shouldn't be less than that. So let's do if builder.stack size set. Oh, there is no set. I'll just check that. Builder.stack size is larger or equal to remove too much from the stack. Indeed. That's what I think. Yeah. Okay, so compiling store. Stack size is 40. So we are compiling this thing into position 40 on the stack. That is 8 bytes. So this 3 thing will be compiled into position 48. Makes sense. And 3 was 9 bytes in size, which is weird, but sure. So 9 bytes extra would be 54, 55. Then we are compiling this number, this 4 thingy. And we have computed this, like the data and the pointer. So I think something in here is going wrong. Wait, what? Okay, so cursor 0. Stack size 57 for some reason. Okay, sure. which the stack should be aligned to 8. For example, 56 is divisible by 8, yeah. And then we compile the pointer. Which should be 8 bytes in size. And then, even after advancing the cursor, so in the second iteration of this loop, the stack size is all messed up. Okay, let's see, push 8 from stack. Is something we do. Push 8 from stack. Push 8. Then add 8. Push 8 from stack and store 8. What should happen? We should have 8 on the stack, another 8. Then add those together. Only one int extra. Then another 8. And then store consumes both of these with a neutral stack size. Okay, so push 8 from stack. Push 8. This, oh look at that, this increments the stack size by 8, but this by 1. That's wrong. Okay, let me maybe go through these functions again to make sure they are all correct. Add 8. Minus consumes 2 numbers, adds a number. Same with sub, mul, div, mod. Compare 0, consumes 1 number, compares it to 0, pushes the ordering, correct. And consumes 2, consumes 2, consumes 2, and I'll push 1. Okay, padding adds to the size of the stack the amount of padding. Makes sense. Push 1, pushes exactly 1 byte to the stack, pushes 8 bytes to the stack, push 1 from stack. Here it goes somewhere back in there, and pushes 1 byte. Push 8 from stack, goes up also somewhere back on the stack and pushes that. Okay, pop decrements the stack size by that amount. Pop below top. Pop below top. Decrements it by the amount. The malloc consumes alignment and size, pushes an address. Free takes alignment, size, and address. Store takes the value and the address. Store 8 value and address. Load takes the address, pushes the value. Load 8 takes the value, pushes the value. It takes the address, pushes the value. Crash. Gotta figure that out. Jump doesn't change the stack. Patch jump, sure. Jump table placeholder. Consumes 1 byte, yeah. Then calling, we have the stack diff of the called function. Maybe let's call this like fun stack diff. Yeah. And this right here, like push call. Oh yeah, that makes sense. Push placeholders, beautiful. Push something to the patches, nice. Push indirect increments the stack by 8. Let's call this fun stack diff. Okay, yeah, that kind of makes sense, I think. Yeah, the free waffle thing. Okay, no, this makes sense. kind of need to adjust the waffle to give us more information about how to correctly generate code. In particular, the free thing here. Free should not just take a pointer, but it should actually take, well, you know, the pointer and alignment and so on. And how does malloc work, by the way? Aggregate, switch, call indirect function pointer. Add, subtract, mul, add, or, XOR, oh, here, malloc. Okay, see. Just takes the size. Yeah, I kind of need to change this so that this accepts the size as well. Okay. Yeah, but I won't do that today. Some other day. I'm back. Next I want to look at the free instruction, because free now expects the size and alignment. That means our waffle free also needs those. Yeah, waffle free returns a waffle expression kind free of some expression, and this should not be a pointer, but instead we should, well, there should be like, where's the is pointer? Yeah. Instead I want the expression size to be, well, 17. Because it should be, let me maybe put it like this. Because that should be the, let's say the pointer plus the size plus the alignment. Hang on, alignment. Yeah, okay, malloc also doesn't have an alignment, so I think let's just omit that. But it should be 16 bytes. The actual pointer and the size. Yeah, okay. And I guess let's try to compile that. See if that works out. Oh, hang on. Yeah, this is still the same, I think. No, this worked. I expected pointer and size should be the error message. In waffle free, creating the waffle and to waffle. Yeah, true. At some point we create. Never mind. What? Oh, I see. That makes sense. In here. Yeah. We want to freeze some pointer. Then we need to know the size. Yeah. Hang on, how does that work in the pesto? Where's a free in the pesto? We have some sort of cast, drop. This should freeze something here. Well, that's also not enough. That also needs to this freeze 3, and 3 is, where's 3 defined? it's used. Oh, it's here. Ah, okay, yeah. So we don't have enough information to know what size of value this 3 represents. So in the pesto already we have to adjust that. And in the pesto, freeze a pointer size aggregate. Now let's not turn that into an aggregate. Let's say this is just free. It's a bit more self-documenting. Pesto free with a pointer, which will be pesto ID, I guess, yeah. And a size, which will also be a pesto ID. Most likely that will just be an int, but in some cases we don't know how much memory we want to free. At least in the future, when we have like arbitrarily sized buffers and so on. Alright, so we'll even need to adjust this, the pudding to waffle. Okay, in the pudding we definitely have enough information, because we only create this at the point where we create the drop function, where we still have types. And here we really want to have some sort of pesto free, where we have a pointer, which is the parameter, and the size is something. But what is the size of our value? We have some type. We extend the type by 1 level. Fair enough. Say type to pesto. Yeah. We have these pesto bodies. And if that is a pointer, then we do this. We actually just compare that to 0, we switch on the result, and if the reference count is 0, the new one, then we load the value. Okay. Then we call the drop fun on that value. And then we free the original outer param. Okay, I see. So this is really the, yeah, this has the type. Basically the size of this type. Value dot type. Dot size. Hang on. Do we know the size though? We haven't like memory layouted stuff, I think. So how does malloc work? Oh, we don't have malloc. We have box. We have new. I see. where pesto up.new of some closure. I see. So the concrete types, the concrete sizes, we don't yet know them. Instead, we only know the type, and that is later on used to calculate how much memory we need to allocate in this new case here. Because we know the type of this pesto ID. Here we only have a pointer, so we need to know the type of what's behind that pointer, so that we can then later on free the correct amount. That makes sense. So this would just be well, it doesn't have it. It just has a type, which is the values type. Yeah. I'll probably need to adjust this then, I guess, for buffers later on, but that's like a problem for future me. So yeah, value. Oh, that's probably the ID already. So we need builder.get builder.typeof. Is there something like that? No, builder.get something.type. Yeah, that makes sense. Okay. Yeah, this is somewhat expected, I think. Oh, it's just another place in here where we don't do the correct thing. So we have the pointer, and we have the type, which will be where are we? Compile closure free fun. Okay. So we know the captured types. We know the closure type. Okay, and that's behind that pointer is the closure of the closure type. That makes sense. Yeah, writing pesto probably. Yeah, pesto free. So in the pesto, the free has a pointer and a type. So when printing the pesto down here, what is this? Interesting. When printing that, we have this free thing that then has a pointer, maybe colon for the type. I don't know. Okay, so we have this mapping.get. Oh, with a pesto free. No. Ah, I see. So in the next compiler stage, in the something pesto to something, pesto to waffle, yeah, we have this free thing in here. Oh yeah, then that free thing has a pointer, and it has a type, which we can get the size of. Oh, memory layout.size. Boom. So we know how much memory is there that we need to free. That's pretty great. Okay, this call doesn't work. Waffle free. Because it has the wrong number of arguments. Oh, do we need to wrap this in an aggregate? Probably. Although it is weird. That's maybe... Yeah, I mean, these waffle int operands, it's also... like the waffle sub, waffle add things, they also create the aggregate on the fly. So I think for waffle free I also want to just have a pointer and a size And then we can also have these nice, very nice cleaner. Yeah, that's a lot cleaner. And this would not be some expression, but this would be a waffle aggregate of, well, the pointer and the size. Or something like that. Although that doesn't work because I would just need a, oh, these individual ones need to be put on the heap, I think. Let's see. No, left and right, they are just waffle expressions right here. Oh, I see. This entire aggregate needs to be put on the heap. That makes sense. And the list takes care of putting those items on the heap. Okay, so now this doesn't work because this is an int and not an expression. Fair enough. This needs to be a waffle int. Okay, to do pointer size, that is something. Oh, now we we've successfully converted stuff into waffle. I think. Maybe. No. Yeah. Yeah. Yeah, here we are compiling to ground. But before that we have a nice clean waffle. And this free thingy here, it takes the pointer to free and the size. Which, hang on, that does need yeah, okay, I guess that's fine. I was wondering, like, do we need the to add the reference count to the size? But I guess in the next compiler stage we'll do that, because here every allocation is, like, implicitly has a reference count. Yeah, okay, sure. So pointer size when compiling the waffle. So basically in waffle to something, we want to have some pointer size thing. Okay, so we have a free thing. We changed the waffle so that it also gives us the size, and the alignment is always 8. So we know that free has, this has an aggregate. And then we know the size. The size is just the, oh, hang on, this emits pointer and size, aggregate of pointer and size. Yeah, same here, it just compiles the arguments and then it pushes this add 8 instruction, because the arguments already have the correct format. The free instruction, what does that need? Ground. I think rather, yeah, let's look at this. So free pops an alignment, then a size, then an address. Okay, so on the stack there should first be the address, the pointer, then the size. Amazing. Then we want to add 8. Yeah. Seems weird to do that at runtime. How does it work for the new thing for allocating stuff? Yeah, malloc. Hang on, in the Waffle? Oh, yeah, in the Waffle, hang on, let me check out the something to Waffle. And in particular the malloc. Okay, yeah, here we already incorporate the 8 as an extra thing that we malloc. So when freeing memory, yeah, we should also have the 8 in here. So we want to free the reference part itself too. Okay. Yeah, that makes sense. And then we also pop, we push the alignment. Yeah, and then we do builder.free. Boom. Nice. Huh. Okay, that is something. So let's next look at printing the ground, because I think there should be some more new lines here. Yeah, between all empties, between all the lines. So this usual spiel of like, if this is the first one, then we set first to false. Otherwise, you just add an extra new line. Okay, yeah, that is the ground. Wow. I mean, that is pretty cool. You have all your instructions here. They do stuff. And they kind of, jump to instruction 230, boom, and then here you do some other stuff. I mean, that's kind of crazy. Yeah. Okay. But we have the entire bytecode. That's pretty cool. Okay, in the Plum file, we want to print that with a new line afterwards. And also, let's maybe look at probably the print line that. The thing is, the ground always starts executing at the beginning, at the first instruction. However, in our waffle to ground thing, the way we do that is we just go over all functions, I think. Where's that? Here. Yeah, we go over all functions and then compile the functions. And then, we fix the patches and that's it. Yeah. What we really want to do is make sure that the main function is actually the first one to be compiled, and then all the other ones. I think. Yeah, oh yeah. It says put main at the beginning of the bytecode. That's exactly what we want to do. So let's maybe do stuff like, yeah, let's just special case that, like entry point is just this, and we need to also like make that customizable somehow. Okay, and then the entry point is going to be at index 0. And then we do, oh, hang on, waffle.funds. Yeah, that is map, so we can just get the key. Okay, so we can do fun dot, oh, hang on, waffle.funds.get entry point. That gives us a function. Then we compile that function on the builder. Amazing. Yeah, then we compile all other functions by just checking if the function key, if this is the entry point, then we just skip that. Okay, and that guarantees that the main function is at the beginning of the bytecode. Okay. And yeah, actually, I think I'm gonna try out a simpler, and another thing that like creates lists and allocates memory and stuff, but just to make sure that this is working in principle, let's do something a bit smaller, like a simple mathematical calculation here. Okay, yeah, that is smaller bytecode for sure. Okay, so what do? This is the main function. The first thing we do is we push 8 bytes from the stack at offset 0. So on the stack we expect our argument to be the A. And we push that for some reason. Sure, we can do that. Then we can push the 2, we push the 1, we push the thing on the stack at offset of 8 bytes, aka skipping the 1 and then pushing the 2 again, then pushing the 1 again, then you guessed it, pushing the 2 again, pushing the 1 again. Yeah, and then calling instruction number 18. Oh, look at that, that's probably the plus function. So instruction number 18, that now on the stack there's the 2 and the 1. So we push those 2 again. We pop the second one so that only the 2 remains. So now on the stack we have 2, 1, 2. Then we push instructions again, this time from offset 16. So basically copying that 2, 1 again. So we have 2, 1, 2, 2, 1. Yeah, we skip the top 8, aka the 1, and pop the 2 below. So now we have 2, 1, 2, 1. Push those again to give us, well, 2 and 1 again. Then we multiply those. Oh man. Yeah, okay, so now we have the result from multiplying 2 and 1. We push that again to the stack, and then we pop a lot of stuff below. A lot of stuff. Yeah, and I'm just gonna assume that this is the correct amount. We skip the top integer, the result that we want to return, but apart from that, yeah, we just return, boom. So here we have called that multiply function, and the result is now on the stack. So now we push the 4, and we have a couple more push instructions. This copies the result and the 4, so the 2 and the 4, and this copies those 2 ints again until we finally call 31. 31 is down here. After the return from the multiply function, again, duplicates those, pops stuff, duplicates that entire thing again, pops stuff, duplicates those again, adds stuff. Yeah, and we push 8 from the stack. The result of adding those. We pop stuff below and we return to the main function. Amazing. Which is after this call, so we push that result again, we pop all the odd stuff and we return. Amazing. So yeah, we do a lot of stack operations that are completely unnecessary. I know why we do them, but it is difficult. So let's actually look at the waffle. So this is the waffle, which seems reasonable. And when we do something like this, we have the arguments on the stack. Each of these local variables is actually allocated on the stack. So I have some space on the stack for that. Which means that first of all, we copy the entire arguments aggregate onto the stack, just to then extract the first argument. And then we copy that entire thing on the stack again, just to then extract the second argument. And those two live on the stack. So then we create this aggregate, which we have to kind of get these local variables, put them on the stack again, and pass that to the multiply function. And the thing we want to do, I think, is change it so that the waffle is more tree-like. Basically not having local variables for everything, but instead just inlining that directly in here, and inlining this one directly in here. Or here, for example, when calling something, we don't want to build an aggregate on the stack and then copy that entire aggregate again to then call that function. This here is only used in this function call. So we want to inline this right here and just basically resulting in bytecode that somehow gets the two. Or we can even inline these. So we can just imagine in here you just have opening curly brace 2, 1, and closing curly brace directly in here. That would mean basically pushing a 2 to the stack, then pushing a 1, and then calling multiply. The more tree-like we do, we make the waffle, the better the stack code will be. But that's a future video. Right now I just want to focus on getting stuff working at all. But that's basically a technique that we'll use to radically trim down on these push and pop operations, because the majority of the code is pushing and popping stuff, just moving data around, wrangling with the stack. The only thing this program is supposed to do is multiply values and then adding them, and this does not reflect that. Okay, we have that. So yeah, that is future work. For now I want to focus on serializing this, so we can execute that with our VM. I think in the I think I'll add a separate file for that, I guess. Either that, ground some file like ground to bytes or something, or just put that down below here, because the binary, the binary file that we generate, that is a ground file. So yeah, ground in here is represented as the size of instructions, but actually the ground file is just bytes. So I think just like we have a write function, we can also just have some sort of 2 bytes function. That returns a slice of bytes. Nice. Yeah. So that's also, like, some of these compiler stages, they do crazy things, you know, like tracking which variables are visible, parsing stuff, like that's really involved. This right here is just, it's in complexity, it's quite similar to printing stuff. I wouldn't even call this like a compiler transformation, like a compiler stage. It's just serializing that. Yeah, so we want to build bytes, which will be a list of bytes. And then basically we want to go through the instructions. And, well, convert them to bytes. So that would be, well, we just switch on the instruction. Oh yeah, and then we'll need to do something very similar to this. Yeah, where basically an op instruction pushes, let's turn that into a reference, I guess. Pushes a 0 byte. Ooh. Yeah. Oh, I think I can use this to use radixes. Yeah, the syntax highlighting is a bit messed up. But basically have the radix and then a hash sign to indicate. Yeah, this is actually just the radix, and now comes the real number. And then comes the number. And the order for the printing is all messed up, because we changed that. Let's adjust that. We have arithmetic, A instructions, we have B instructions, the bitwise ones, we have C, the stack control instruction stuff. Then we have D, the data instructions. Then afterwards E, the error instructions, the crash. And then F, the control flow instructions. Yeah, let's do something similar here. We have, well, let's just copy that because I haven't really adjusted that yet. Okay. Okay, adding something, that would be A0. Opcode A0. Subtracting stuff. Let me maybe do it like this. Yeah. Subtracting stuff is A1, A2, 3, 4, and 5. Okay, now come the bitwise instructions with opcodes B0, B1, and B2. Next, pushing padding. Which would be, well, oh, the first instruction with an argument. Interesting. Yeah, that would be C0, and yeah, it has a byte, and then also the amount, which should be a byte. Yeah, then pushing a byte, that would be C1, and then pushing the byte. And pushing 8, bytes, aka pushing a 64-bit integer, that is C2, and then pushing the integer. Well, yeah, actually, like pushing the pushing the bytes of the integer. How do I do that? Integers are little endian encoded in Martinez. So I think I'll just take a reference. I don't know if this is hacky. Probably. Take a reference to that integer which lives on the stack. Cast that from a reference to an int to a reference to a byte. And then 8 times I just push the reference. I think there's like an add or something. Hang on, Martinez stat library mem, I think. There was add stride offset. Oh, look at that. Assuming multiple instances of tier safety memory next to each other, aka multiple bytes in our case. Return a reference to the item at the index. Yeah, that is the address of this reference plus the size of the t. In our case, that's a reference to a byte, so that's just 1 byte times the index, converted back to a reference. So we can do add stride offset of I, giving us a reference to the ith byte and dereferencing that. That is hacky. Yeah, like I should be able to do some math stuff, you know. Okay, so ref is, whoa, oh, I see. Martinez automatically dereferences stuff. Like if you have, you know, an ampersand list and you do .get, which is only defined for list, that automatically dereferences the get. And the cast function for int is not defined for reference of ints, but only for ints. So it actually dereferenced that. Yeah, we want to cast those references. That makes sense. Okay, so then pushing 1 from the stack. Yeah, that is just bytes dot push C3. Should have copied that from above. And then basically the offset is an int. Okay, let's maybe have some sort of helper function. Bytes of an int. Little endian bytes. And that just does this, which I think is fine. Oh, let's do something even better. Let's have push little endian bytes on a list of bytes. Yeah, like that. And then we can just do push 1, push 8, and bytes dot push little endian bytes of that int. Amazing. Similarly here, push little endian bytes of the offset. Yeah, push 8 from the stack is gonna be pretty similar with C4. And little endian bytes of the offset. We have a pop, which is a C5, and then it's just a byte telling us the amount to pop. Then we have this C6. Yeah, I'm not entirely sure about that one. Let's go look at that. Push, pop, pop below top. First has the amount of bytes to skip, and then the bytes. Okay, so the bytes to skip would be tuple A. I should probably type that at some point instead of just having a tuple with A and B. Then memory stuff, allocating stuff is just malloc. Yeah. Freeing is just D1. Storing 1 is D2. Storing 3. Storing 8 is D3. Loading stuff. And that. Just realizing. We could even go further and say allocate and free. And store 1 could be D1, store 8 could be D8. We like even have, not just have the first hexadecimal letter kind of be a mnemonic of which kind of expression that is, but have the entire expression. I'll think about that. That is such a niche quirk, but it's like that would be pretty cool, I think, if those make some amount of sense. Okay, so this would be E0. Then jumping to a target. Okay, this is actually interesting, because when serializing this, the bytecode doesn't expect an index of an instruction. It inspects an offset into this bytes thingy. That means that we'll need to find out where's that instruction. So we'll actually need a mapping. This looks less and less like a straightforward serialization, more like okay. Instruction offsets, I don't know. Like a proper compiler stage. So the instruction offsets will just be a list for each instruction at which offset it is. Let's just call it offsets. And then patches is going to be a list of tuples. Int with position to instruction index. So this basically says at offset, I don't know, 50 in this byte thingy, we actually want to point to instruction number 20, but we don't yet know where that's going to be in the bytecode. So after lowering all the instructions, after converting all of these to bytes, we'll have to go over the patches and adjust the bytes, kind of fix these up so that they point to the correct offsets. All right, which means in here we can just do bytes dot push little endian bytes 0. That's a placeholder, and then we do that is Yeah, sure. And then we do patches dot push the tuple of the offset right now, which is going to be bytes.len before pushing that, and the target, which is the index of the instruction that we want to jump to. Yeah, very similar for the jump table, although it's even more complicated, because we'll have f1 in here, and first of all we push the bytes.push table.len, okay, and then basically for each target in the table we do this. Yeah, for calling a target, well, that's probably going to be f2. Imagine this is fc for call, like that would be so cool. Oh, that would be nice, yeah. Okay, so we push f2 for calling something. Let's actually make sure these, I'm just, you know, I don't know all of these codes by hand, so. Okay, so we have f2, we push a tuple of the bytes len and the target, and a placeholder, okay. Push indirect, pretty similar actually. Set f3, do that, then call indirect is just a single byte. And finally return, that is f5. Yeah, I know that, that's correct. Okay. And then afterwards, for every patch, oh hang on, we want to fill the offsets. So before each instruction we actually want to do offsets dot push bytes.len. Yeah. And then for the fifth instruction, offsets at position 5 contains at which offset in this bytes thing instruction 5 is. So we can now do for every patch we do bytes dot, we want to replace that basically. That is interesting. Yeah, not push that, but replace that. So we have this offset, and we have an int. And we want to set the thing at offset plus I to that byte. Yeah, makes sense. Bytes dot replace little engine bytes at patch dot a, which is the offset, with patch dot b, which is the target, and we want to map that. So we do what was it? Offsets. Yeah, offsets dot get of that. Yeah, that seems correct. But in the end, we want to return the bytes to a slice. Oh yeah, we don't call that yet. So in here, we'll actually need to count to bytes. Boom. Now let's print them for good measure. Why not? Oh, I see. Yeah. So in here, the table len is actually, we know that the table has a maximum length of 255 for jump tables. So we can do that. Ooh. Nice. Yeah, let me take a quick break. Okay, I guess let's write that to a file and yeah, go from there. So is there like a write file or something? Oh, there was read file. Yeah, okay, so there was probably also write file with, I don't know, output.count. And we'll put the bytes in there, please. Okay. There's an output.ground file. Okay, yeah, running that does not. No. Okay, sure. Let's maybe debug that by opening it up the ground VM thingy, and maybe printing the opcode that we want to execute. So that would just be the opcode. Oh, right, so we need to basic build, I think. And then do that. Okay, but do we now have opcodes? Yeah, we do. A single one. Well, I guess better than none, yeah. Let's print that in hex, maybe. Ah. Well, that's kind of a pain to do. Well. Okay, so we have C4. That's an interesting opcode. Hang on. Really? Yeah, I guess let's first kind of double check that and make sure this looks reasonable in a hex editor, and then yeah, I think hex minus C does that. Okay, yeah. Oh, so we do start with C4. Oh yeah, which pushes something from the stack. Makes sense. Oh, I see. I see. Our program expects something to be on the stack, because our main function expects an int. However, the ground VM it actually runs that program with an empty stack as the input. Initially empty stack. So let's maybe put something in here. Let's maybe put a 5 in there. In a little endian encoding. One, two, three, four. 1, 2, 3, 4. Yeah, that is 8 in length. Yeah, okay, so let's compile that. Which means that the ground VM written in Zig will run our code with 5 as the input. Okay, and the program outputs with a 6, which probably makes sense. Let's look at the playground file again. With a 6, yeah, because 2 times 1 is 2, plus 4 is 6. Nice. That is nice. Let's do some more complicated stuff. Let's say that we really have a list here, and hang on. Maybe let's say we have. Well, I do want something with memory allocation. I'll say make list of with 2.len, please. So compiling that. I think a makefile would make sense to do several things, but basically I don't want to recompile the compiler every time, even if I didn't change the compiler, if I just changed the program. Yeah, oh, that is massive, but sure. That is compiled into something. Optimizing the waffle is really something that we should do. Yeah, how big is the file? It is like 4,800. I mean, fair. I think we just set 1,000 is our limit right now. So let's change that to maybe 10,000. I don't know. Compiling that, running that, out of jump table bounds. Okay, yeah. Okay, there were still bugs. I get that, but I think actually, like the best. I'm kind of struggling with these bugs because the possibility where they can be introduced is quite big. You know, these kind of bugs, they need to happen somewhere after the pesto, because there we still have, well, somewhere after the, was it the pudding? Yeah, so either in the pesto or the waffle or the ground. And these conversions between those, they are quite complicated. And the problem is there is so much noise in the generated code. There are all these push and pop instructions here, so many of them. So it's really difficult to kind of get a grasp on that and kind of figure out what's going on here. And that is why I'm actually, I think I'm going to end the video here and look at optimizing the waffle and, you know, basically making it so that more efficient bytecode is generated, not just as, you know, a way of, oh, now we're optimizing stuff even though it's not even working yet, but that will also help us debug that. If you trim problems down into some, into the essence basically, then errors become more obvious. So I think even though optimizing is not the goal right now, I think that might be useful just as a way to debug that more effectively. Yeah, so I guess I'm gonna end it there. The simple program worked, you know, the program that just calculated a 6. And yeah, I really want to iterate on this kind of low level stuff right now and make it so that the back part of the compiler basically is quite robust and somewhat optimizing stuff, and so you don't have to worry about the back part at all. Yeah. So I guess that's it for today, and see you in the next video.